So in this video, we're going to cover the basics of stress and strain. Alright, so what is stress? What's the definition of stress in one dimension, and what's the definition of strain in one dimension? So if we have let's say we have a very basic shape, a very basic part, a solid cylinder, that we apply a force along its axis, Fn. Alright, we define the stress within this component as being equal to the force being applied divided by the cross-sectional area. Alright, so for a cylinder, it would be equal to pi, the cross-sectional area would be equal to pi d squared over 4, and that would be our stress. Okay, the strain within that material, alright, for a 1D component would be defined, there would be two strains that would occur. So if we apply a normal force to this component, it's going to cause the cylinder to extend out, and it's also going to cause its diameter to shrink. So we can relate those two physical phenomena using the strain values for the system. So the strain along the axis is going to defined as the length of our the cylinder after it's been stressed minus the original length, which was the length when there was no force being applied, divided by the original length here. All right. So in addition, the lateral strain is the strain due to the contraction due to that applied normal load along the axial direction. So we have the diameter, the difference between the diameter in the final case divided by the diameter of the original diameter. Okay, so typically the lateral strain is going to be a negative number because the final diameter will be smaller than it. All right, and then we can define the Poisson ratio, which is another material property, as the ratio between the lateral strain and the axial strain. So typically Poisson's ratios are between 0.2 and 0.5. All right, for most engineering materials. Okay, so we can relate stress and strain within materials along what we define as the elastic region, and this is where most parts are designed to remain. All right, so within the elastic region, the relationship between stress and strain is linear. So if we know the strain, we can calculate the stress if we know the material's Young's modulus. And all the Young's modulus is the slope of our stress strain curve for a given material. Okay? So if we know the strains, we can calculate the stresses, and we're good. We're good. So we talked about the difference between lateral. Just in the last part of the video, we talked about lateral strains. We talked about the definition of Poisson's ratio. The last thing related to strains that we can talk about is the change in the volume due to a stress. So the change in volume is referred to as the dilation of a material, and we can calculate that change in volume compared to the original volume by taking that lateral strain that we defined above, and we can multiply it by 1 minus 2 times the Poisson's ratio to calculate that volume loss. All right. So a lot of times in engineering systems, we have more complex stress scenarios than a single axial loading. So in those cases, we might often come into a case where we have 2D or 3D stress strain relationships where we need to calculate the stress in more than one direction. So for those types of cases, in order to calculate our stresses and determine whether or not failure will occur, we need to understand the relationships between stress and strain in multiple dimensions. Okay, this is often referred to as being into a state of plane stress. All right, there are 3D stress strain relationships. Well, you might learn about them in MME 412 and 512, but it's beyond the scope of this course to talk about them. All right, so if we know epsilon x, epsilon y, and we know the material properties of our system, our Young's modulus, and our Poisson's ratios, all right, we can calculate the stresses sigma x, sigma y, All right, and then the last stress we have is a shear stress tau xy. Now, in addition to our linear strains epsilon x and epsilon y, we also have our shear strain gamma xy. All right, so we'll talk about in today's lecture. We'll talk about how we can determine epsilon x and epsilon y and gamma xy using strain measurements, and if we know epsilon x and epsilon y and gamma xy, we can calculate sigma x, sigma y, and tau xy, and we can determine a factor of safety for the given material. If we know the material's yield strength, we can determine its stresses and its stresses in the sigma x, sigma the y-axis, the x-axis, and as well as the shear stress tau xy. So if we know all these things, all right, we can then determine a factor of safety, all right, using something called the von Mises criteria, or we can use something that's called the we can use the what's called the Tresca criteria. All right, these criteria are beyond the scope of this course, but you'll use them in MME 312 a lot to calculate to determine the factor of safety for a given mechanical component.